Welcome everyone to this seminar series by the Nuclear Particle Physics Society. Today we are joined by an icon in the Manchester Physics Department, Dr. Paul Campbell. For many of you, Dr. Campbell will need no introduction. For those of you who don't yet know, he's a senior lecturer here at the University of Manchester and probably best known for his enthusiastic and entertaining delivery of the electromagnetism module in second year. Today though, he won't be talking about B fields and the Ampere-Maxwell equation, but he will be discussing the shift to remote working and how that will affect future research in the field of nuclear physics. Both the talk and the Q&A afterwards will be recorded, assuming we've got time for a Q&A. So if you want to ask questions afterwards, feel free to unmute yourself if you feel comfortable, or pop a question in the chat and we'll read it out on your behalf. Also, make sure to keep an eye out next week for our final seminar of the year, which will be presented by Professor Heather Gray from Berkeley, University of California. We'll be discussing her research into the Higgs boson, which will be really interesting. So make sure to come to that, and I'll put a link in the chat in a minute. After the talk, I'll invite you all to unmute yourselves and we'll attempt a Zoom round of applause, which is always interesting. Okay, I think that's all I wanted to say. So thank you for joining us today, Dr. Campbell, and I'll hand over to you.
Thank you very much. That's a very polite introduction. In fact, you could see some people have managed to join because I don't know how many we get in week 11, so busy time for everybody. Let me switch over to the talk as soon as I can find it. And get going on this. So I've kept it more general than just how we're going to approach things in the future. But Peter, just to check, before I start, can you see and hear everything okay?
Yep, loud and clear.
Oh, good, excellent. So I've kept it a bit more general than just what we're going to do in future. As I'll soon show you, we're compared to things like sort of CERN large-scale experiments, a tiny, tiny scale. So these are experiments you build and run yourself, and typically we sit next to our experiment, maybe slightly radioactive, but hopefully not too big a concern. But this is an experiment you conduct, and a sort of a big collaboration for us is something like 20 or 30 people. So slightly different scale to other activities you might hear about at CERN, but say an experiment you run yourself. Of course, I'll be talking about what used to happen primarily because since, well, not March this year, but March last year, we've been in the same boat as you. So normally I'd, I'm just trying to move something, whoops, get that off the screen share. Normally I'd be trying to tell you about my sort of recent activity at this beautiful lab here. It's a lab in central Finland, the University of Jyväskylä Accelerator Laboratory. So this is in central Finland. It's not exactly on a lake, even though it, or not exactly an island on a lake, but it's pretty close. And primarily you access over this bridge. And that's normally where I'd have been for about 4 or 6 weeks of my year. And of course, there hasn't been any of that this last year, unfortunately. So in the UK, and with all, in common with all UK groups, all our research is done around the world. So we work at different, LSF is a large scale facility. So for a lot of us, that's CERN, and I do some work at the Isolde facility CERN, but others in the group work in America, so Argonne National Lab, you'll hear, Jefferson Lab, and a whole range of EU countries. So labs in France, as you just heard, in Finland, and dotted around the whole of Europe, and all of it essentially got cancelled. Or so we usually, when you buy a ticket, travel to the lab, take your equipment with you, set it up, and run your experiment. Or maybe you have it semi-permanently installed over there, but whatever you're doing, you travel over, and that, since March last year, hasn't happened. So exactly like it's hit your university experience, we've been a bit hit, or exactly the same clobbered on the research side. And I'll show you a little bit about what we did, but mainly concentrate on what the type of experiments we usually try to run, and what we'll be doing in the future. So there's an example of bad impact of, in common with most of you. I've been staring at Zoom, often a picture of myself for endless hours waiting for something to open up and then join an experiment via Zoom. And that's not the way we run. We, by the way, don't run experiments remotely. We don't sort of sit in an office or control room running on a computer. You build and run your own experiment. You take it to a lab, and your lab experience includes something like this. This, by the way, is us going for lunch. So across a lake which is frozen for about half the year. This is central Finland, by the way. So a quicker route to get in and out of the lab is just to walk across your frozen lake if the time of year permits. Fast access to your experiment. So what would I say? Last year, we had to go to remote running, just like you had to go to remote lectures. No choice. The only other option was to shut down entirely. It worked. So we ran 3 experiments entirely remotely with us over Zoom and local people working there. What that involves is people ripping out a corner of the room, reinstalling a whole range of new control electronics and control computers. We've got that all set up, and us zooming into the experiment with these people, the locals, working around the clock to try and facilitate experiments. So that worked. Actually, it worked rather successfully, but I'll come back to that at the end. So we have to worry about what we're going to do in future. So Quo Vadis, St. Peter, or Latin for which way are we going? But I'll come back to that at the end of this presentation. Let's have a talk about what we more normally do. So this is a massive change for us and the way we run experiments. Just to give you a scale, you'll see a person in this picture here sitting next to an edge of this is a high voltage cage. So this thing here is about 3 meters tall, and that's a scale of a reasonably large experiment in nuclear physics. It's receiving beam from a target site that's buried behind this concrete wall, and that's being driven by a cyclotron beam that's delivering something like 1 to 10 microamps. We measure beam and current when you've got quite intense beams of protons, maybe 50 MeV, hitting perhaps something like uranium and producing fission fragments or nuclear reactions. And we're taking these and taking them down to an experimental station that you sit next to. The radiation hazard is very small here. Much more of a concern is the high voltage and laser hazards that I'll tell you a bit more about in just a second. So all of this, what I've cut off here is us trashing our equipment last year, trying to set it up for remote running and doing what we could to stay in business while we have to cope with not being able to travel. The facility is called the Isotope 4. I'll come back to what that means. An iron guide isotope separator online, and it's the 4th version of this. And I'm conscious that we may have some 1st and 2nd years here. So I'm just going to say a few general words before I talk about the facility. Because what I actually do, and it's about half the nuclear group nowadays, do is optical spectroscopy of the nucleus. And that's wrong, or that shouldn't work. So optical means your sort of visible light, or maybe in the ultraviolet, and that interacts with atoms. So that's something on the scale or wavelengths of hundreds of nanometers, and the nucleus is 10 to the minus 15 meters. So these things shouldn't talk to each other. They do though, and we exploit it in order to do our experiments. So I'm just going to say a few general words. Apologies to some of the older students, but just as a general introduction. And also, this is week 11, so we don't want anything too taxing. You've got other things to worry about soon. So bit of nice reminder of hopefully things from the old days. If you burn chemical elements, you get these beautiful distinctive flames. I'll concentrate on sodium and then potassium in just a moment. You put that through, this is a handheld spectrometer, so just a prism, and you'll see actually that light from sodium isn't just the orange light you associate with street lights. There's a weak green light coming out as well, and there's actually other things which are harder to see in this spectrum. If you do a better job than this handheld spectrometer and zoom in a factor of 1,000 on that line there, you see this. This is the atomic hyperfine, the atomic fine structure. So we zoomed in a factor of 1,000, and you'd see that that line is made out of two components. They're called the D1 and D2, and they were picked up very early on in the history of atomic spectroscopy. And these are what you understand by some of the things you heard about a couple of weeks ago from Mike Lancaster, the electron's magnetic moment, or the interaction of the B field produced by the electrons with the electrons themselves, with their angular momenta, resulting in a splitting that we see at about the part per thousand level in your spectrum. What you do next is you zoom in about another factor of 1,000. And if you zoom in, and I had to cheat here, this is actually a potassium spectrum, not sodium. So just a little reminder, your transition here, you're talking about 10 to the 15 hertz. If you're talking about something like 300 nanometers, that's just into the ultraviolet. You're up at 10 to the 15 or petahertz. You've zoomed in by about 10 to the 6 or 10 to the 9 times. So a million or 1,000 million. And you see that component that's split into two, pick one of them, and it again splits. And actually in potassium splits in, this is actually 4 lines, but 2 of them are unresolved from each other. There's this tiny hyperfine splitting, and that's the nuclear perturbation on the atomic structure. So in the world of chemistry, all isotopes are the same. They'll happily tell you in chemistry, it doesn't matter which isotope you've still got chlorine or you've still got potassium. If you go in your physics studies, in 1,000 million-fold intricate part per billion spectroscopy, you can see the different perturbations the nucleus is having on your atomic structure, and that gives rise to this splitting here. Missing out the details, so you can learn things about the nucleus by doing this incredibly precise spectroscopy. And it has a very, very long history that I'll tell you about briefly over the next couple of slides. For people in their first and fourth year, we're going to go in and have a look at the hyperfine structure, isotope shifts, isomer shifts. If you're in your first and second year, what's perturbing that spectrum is the fact that the nucleus has finite mass, so it's not an infinitely heavy system that's being orbited by an electron. It's got a finite volume as well, and that's curtailing the binding of the electric field over the nuclear volume. It's also got structure. So as you were hearing about, I say a couple of weeks ago, magnetic moments, it's not a point-like entity. It has charge structure, and those charges are in motion. I'll come back later to why we do optical work. And again, for people in later years, a typical nuclear reaction, we measure in a unit, a rather old unit called barn. If you compare that to an atomic cross-section will be about 10 to the 15 times higher. So a much higher probability of interacting with your system. And I'll try to convince you, show you it means in a few nanoseconds, you can guarantee you've interacted with an atom or an ion of interest. That's easy enough time for you to ensure 100% probability of interacting with the system. But more on that in just a moment. Right, a little bit about some ancient history. Urey found deuterium in 1931, and this is really where, if you had to pick a time where nuclear work started, it started via optical spectroscopy. So essentially, they took a guess that hydrogen, so him and his co-workers, collaborators, took a guess that hydrogen had more than one isotope. They vapor distilled it, just like you would alcohol or trying to enrich whiskey, and then put it through a spectrometer. They had to do this a couple of times, and finally, a second set of lines appeared, exactly what you would associate with orbiting a nucleus that has a different mass. Quite, relatively speaking, easy, about a part per 10,000 shift, and discovered that hydrogen had a heavier isotope. Why was that so important? Well, actually, it's 1931. It was the year before the neutron was discovered. So Chadwick found the neutron in 32, and actually the first evidence was really the year before when they found the deuteron. I should point out also atomic mass measurements were critical at this time, and we actually do both in our spectroscopy nowadays. Here's one that you got from just 2 weeks ago. So you're up now to 1947. Still a long time to pass. When Schwinger was first talking about his radiative correction, so this was a G82 divided by 2 correction, he managed to derive, it was alpha over 2 pi, so the fine structure constant divided by 2 pi. And the way they knew, or they were defending the fact they had the right answer, was looking at this hyperfine structure. Now, actually, the hydrogen measurements weren't very accurate at that time. They had better ones for sodium and gallium, and looking at those were the first indications of these quantum electrodynamic effects. They were picked up through optical spectroscopy. Now, I know he showed you the correction. If you can't remember what the correction is, you can always have a look at his grave, as Mark told you, because he stuck it on his gravestone. So that's more correction. Numerically, it's about 0.001617. He got that, or he knew he was right, from optical spectroscopy of atoms and ions, and looking at the nucleus, or looking at the interactions with the nucleus, and using that as his route in to checking his quantum electrodynamic estimates or corrections at those times. So what does a modern version, why would you still do it nowadays? Well, the reason it was done in the early history, well, they had no other access to it, but the experimental sensitivity and the experimental precision were immediately attractive 50 years ago, and they're still attractive today. And this whole rig, if I simplify it down as much as possible, what happens is a high energy beam comes in here, hits a target, there's a nuclear reaction inside a gas cell, and we form that into a jet and blow it out with the gas, and then strip out the ions and accelerate them down these beam lines. The headline is, we get a nuclear reaction and make sure the products never touch the sides. So it never touches any apparatus. Everything is done in flight. So you have to slow it from the nuclear sort of energies that your recoils are produced at, down to thermal energy, so something like a few electron volts, accelerate them into a beam, and ensure you never touch any of the apparatus. If they stick, you'll never be able to use them. Some of the elements we'll be looking at are things like tungsten or molybdenum, that you won't be able to evaporate them off any metal surface. But more importantly, if you do all of this at about 40 or 50,000 volts of acceleration, you'll get from here to here in less than a millisecond. So if your species only live for a millisecond, you see the early measurements, they were looking at things like hydrogen or deuterium or sodium. They're stable elements or stable isotopes. They last forever. So you've got plenty of time and plenty of sample. What we've got nowadays is next to no sample and next to no time. Your species might only live for a millisecond if it's a very exotic nucleus or a very exotic isotope that's a long way from the line of stability. So keep it in flight, fly it all the way down to your lasers, and do in-flight spectroscopy before it decays. If you do that, and this is direct experimental spectra, so there's no modification here. These are different masses of yttrium. Actually, none of these are stable. Yttrium 89, or it'd be a few ones lower than here, is the only stable isotope of yttrium. All of these are radioactive, and some of these are very short-lived, heading towards, well, I think this one's about 50 milliseconds, but we can go even lower than that in our spectroscopy. This is what this super zoom of a particular atomic transition looks like. Now we've zoomed in again about more than 1 million times, or just to give you a scale, on your screen, if this axis here is 7.5 centimeters, which it is on mine, the origin on this picture is 10 kilometers away to the left. So that's where 0 is. That's how much we've zoomed in. And actually, this isn't too challenging for us. We could go about another 3 orders of magnitude more precise than that if we had to. And then you see why we have such precise measurements for some of these G factors and magnetic moments that you've been hearing about recently, especially for the electron. So this is the nucleus itself. It's actually yttrium. You can pick up some things. Well, first of all, there's this multiple component associated with each isotope. That arises from this nuclear structure. So it arises from the magnetic moment and the electric quadrupole moment. So the fact it's not a point-like entity gives rise to these distinctive fingerprints, and we can interpret these. The centroid, though, is drifting down in this direction. And this is actually right. It's the origin's over here. This is the transition is getting less well bound, but that's because the nucleus is getting bigger and bigger. So we're getting, in volume terms, further and further away from a point-like system, which would be our best bound system. We're looking at an increase in nuclear volume. And then suddenly, something spectacular happens. Actually, we can see it in this fingerprint where the central peak here has moved. It's moved massively over to the left, but the whole centroid has suddenly leapt. And actually, we know what's gone on. What's gone on there is a shape change. So like I said, it's the slow increment here is a departure or ever increasing nuclear volume. Something here has massively increased the nuclear volume, and this wasn't adding extra neutrons to your isotope. This is the nucleus changing shape. And it's these phenomena that you can look at for understanding your nuclear forces. This is a quadruploid, so it's become quadrupolar deformed. And this is a rather famous shape change at the n equals 60 neutron number, and one we've explored rather a long time in our collaboration. But I'll tell you more about what we're doing generally in the future in just a moment. So, very nice direct access to what the nucleus is doing, both what we would call microscopic and macroscopic, so the shape and volume of this thing, but also all of these reflect the valence. So the hyperfine structure tells you about what your particles or your valence nucleons are up to, what orbits they're in, and what couplings they're producing with the rest of the nucleons in your system. As I said, though, none of those are stable isotopes of yttrium. Yttrium's down here. It has one stable isotope, and you've just been looking at data that's on this side of the line of stability, and then we were stretching out to about 102 there. Right over here, we're something like 10 or 15 neutrons from the line of stability. So for people who haven't seen a segue chart before, if you're in the first year, this is not like the periodic table, a much better way of showing it. Atomic number up here, neutron number along here, and the black dots are showing you your stable elements. So your elements are just ranked up in atomic number order here, And diagonally, you can see the atomic mass. Neutron number is drawn out in this direction. How are we getting those very, very short-lived yttrium isotopes? Well, actually, there's two intense production peaks here from proton-induced fission of uranium. So if you hit uranium, which has a rather large neutron excess, and it splits up, it doesn't split up actually into two even fragments. It splits up into two, a light and a heavy one, reflecting some nuclear binding concerns. And they're actually a mile from the line of stability, with a mile being tens of neutrons away. These things will race back. And if you're the general public, this is nuclear waste, or waste that you would have from, or part of the waste that you'd have from a nuclear reactor. Very vigorously beta decaying waste, and it will head back to the line of stability. For us, of course, it's a chance to study a whole range of exotic nuclei, nuclear systems, and actually about 3 or 4 more times than you have stable isotopes. So instead of having something like the 500 you can naturally look at, proton-induced fission uranium will produce 1,500, 2,000. Purely depends on how sensitively you can do your spectroscopy. These are the yields diving off rather quickly near the end. A bit of shameless self-advertising. If you'd like to see a nice review on laser spectroscopy for nuclear physics, you can read a beautiful review article authored by a certain B. Campbell. So that's a available progress in particle and nuclear physics. Could do with an update. That was about 2016. But this shows you across the Segre chart which systems we've accessed. It's not that this isn't just my work or collaboration work here in Manchester. So worldwide effort looking at these, and you can see where you can do it. You can extend right from very, very neutron deficient systems all the way up to incredibly neutron rich systems, and look at the nuclear physics and look at what the nuclear strong force is doing across these exotic species. I don't need to say, like I say, we've got a mixture of people here today. So for people in the later years, formally, this is the mean square charge radius, the dipole moment, quadrupole moment, something called a hyperfine anomaly. That's a distribution of the nuclear magnetism, and the nuclear spin itself of the nucleus under study. We can extract information on all of those. I'd like to go back to this more generally. What you're looking at is sort of fundamental information on the nucleus when you've only got 1 millisecond to do it. So you haven't got long to learn about this system before it's going to disappear. And rather bizarrely, accessing it with light is a really, or visible light is a really intelligent thing to do. So this cross section is enormous, but why is it so good? Let me just talk you through the details of the thing you're seeing here. If we try and do, what we're looking for is resonances. And actually, if you've got very good vision or very good imagination, you might be able to imagine there's something going on here. This is what we refer to as singles. This is you're looking for photons, trying to collect your resonant light, but there's a background and you haven't got very many ions to deal with. In fact, we've only got less than 50,000 ions per second in this test we were doing here. If we can exploit the time of flight, though, of these ions from where they were created to where we're interrogating them with a laser, we know when they should arrive. So if you put a time gate on your photon spectrum, you only accept photons that arrive in the right time to be associated with mass 93. It cleans it up to this spectrum, and suddenly your resonance comes leaping out. You can tighten it even further, try and make sure everything's at the same energy spread, nicely focused in time and energy as possible, so get down to about 15 microseconds. But then you can do something even better, is just demand that you saw 2 photons. Now, the probability of seeing 2 photons randomly in 15 microseconds is this region here, nothing. you'd have to have a huge, intense background to try and get photons randomly. When you're resonantly scattering off an ion or an atom, this thing is like a little lighthouse. It's going off, emitting away, and you've got quite a significant chance of capturing a couple of photons. So if you say, I want 2 photons with the right time of flight, you turn that spectrum into this. And that's, just raw data. This is just taken off the machine that's recording the photomultiplier signal raw. No other corrections, no other dodgy reconstructions or anything else like that. You see that spectrum there. That's why we do optical spectroscopy. The sensitivity is absolutely incredible. You really can pick a sort of needle out of a haystack, or it's like on a battlefield, you can hear the machine gun against huge deafening background noise. Very distinctive patterns or bursts from light sources or audio sources. If you pluck that out, you can get something like this from the spectrum that originally looked like that. Just the last thing, so there's a bias there. It's not just, so there's 2 of us in the nuclear group, so Professor Kieran Flanagan and myself, but as a student-wise, it's probably about half the group involved in this sort of spectroscopy. What my students look at, or one of them in particular at the moment, I show his work, is to exploit this sort of multiple photon, or its multiple optical pumping effect. You want to store your radioactive ion, radioactive atom. You may still only have a few milliseconds, but that's much longer than an atomic transition. So an atomic transition will take place in like 5 to 10 nanoseconds. So actually storing them, even if it's only for a few milliseconds, is, you know, 1 million atomic lifetimes. Or you could get, or put another way, you could get 1 million photons out of one atom if you can hold it and can cycle it. And to do so, and as the electromagnetism lecturer, it'd be irresistible for me to not pick up a little bit of, hopefully fairly straightforward electromagnetism. You get a piece of copper or some nice conductor and drill a hole in it. Bigger at one end, small at another, so a nice tapered hole. Make 2 of those, switch them around, and put something at ground in between. So what are you doing? What you're doing is making the electrostatic equivalent of a skateboard park. So something in potential that looks something like this back bit here, try and make something like that. And actually a glorious bit of electromagnetism is that cones lend themselves to this perfectly, as I'll show you in just a moment. So what we're doing is we're going to create the electrostatic equivalent of 2 of these and pop our radioactive atom, or ion in this case, into these, and it will circle round, and we can try and hold it that way, just electrostatically. Does it work? And the answer is yes. So this is a very, there's a lot of nice bits about sort of simple things in nuclear physics work rather well. So we're trapping an ion beam that's quite low energy. It's only being accelerated through 800 electron volts. Your nice bit of electromagnetism, and I'll show you reality in a moment, is you can actually solve for a Laplace's equation. You put this up at some potential, and in cylindrical coordinates, you'll find along the z-axis, it's parabolic, so it's rising up in z, and along little r, so your radial parameter, is also rising up as r squared. So it is just like a skateboard park, parabolic along the axis, parabolic axially, and you'll create these little sort of like containment pits, and we can circle our beam between it. So what do you do? If you pick a potential just above the beam energy, so 805 volts here, you get these nice, lovely, soft reflections around your skateboard park. By the way, to get it in, you drop the front one to 750 volts. That's lower than the energy, and ions can come in, enter the trap, and circulate around it. If you crank this up, actually goes through a little instability, but then a much higher potential, around 1350, you get what was so-called hard reflections. These are much like laser cavity modes, if people have seen lasers in operations. So very similar concerns for actually the lasers we use in our spectroscopy. So a nice way of holding things in a very easy manner. By the way, just let you in on a secret. So your students, so you'll get forced by EM lecturers to solve Laplace's equation and Poisson's equation. Actually, in real life, what I do is, what we all do is just hand it over to a computer. So it's a numerical. We have as a reminder, we have a unique and a solution for Poisson's equation and therefore Laplace's equation that we can just write down as an integral. That's the sort of thing you do numerically on a computer. And this is a nice example, especially pertinent for us. What we're doing is a mixture here, soft reflection in the back, containing our ions in this back section, hard reflection here, so that we can use the front electrode to get in and out of this system. So, very nice. Does it work? Whoops. Yes. There you are, the result from 2015. So this is actually the ions being injected. 5 milliseconds later, this is us ejecting them out of this little, I say, skateboard park. Exactly what we need to achieve, and the thing's operating very well. And as a little reminder, 5 milliseconds for in the sort of atomic spectroscopy we're doing, that's infinitely long. So the transitions rates about for the species I was showing you about 5 nanoseconds. So you can interrogate this thing 1 million times in 5 milliseconds. So even though it's a short absolute time, which we need for the half-lives we're looking at, it's huge compared to our spectroscopy, and we can get lots of time to interrogate these species. Now, just quickly, I hope you can see this title above. This is how you make impact as a PhD student. And this is my student, Daniel. And what you do is you arrive sort of 2 years ago. Remember, we were doing this since 2015, everything's working. And you tell your supervisor he's got it wrong. You're doing everything all wrong. You should do it this way. And hopefully you can see the difference. Look at this, there's 2 cones facing, and it all works, and it's all very successful. New PhD student says, turn the cone round the other way. And after a little bit of simulation and checking, he's right. So if we turn this round the other way, these are equipotential lines, it's actually every bit as good if we flip this front cone, or as he pointed out. The bit that's very attractive for us, this was at 1350 volts before, but using the short, or this sort of narrower end, you can get exactly the same effect for way less voltage. So only 860 volts. And just so that's before we were injecting at 750 and having to ramp up to 1350, so 1350 volts. We want to try and do that in as few microseconds as possible to capture our nice time of flight bunched beam very precisely. Daniel, courtesy of his nice, simple idea, swap this around. He's knocked that voltage down to a change of 110. That's a power reduction of 1/136, and we'll be able to switch our cone at least 10 times faster. So massive improvement. And when you come up with a suggestion like that, you end up as your PhD is build it, and we'll get it working. So that's what he's doing at the moment, and is desperately keen to get back to Finland as soon as possible. What would we do with this? So I'm just conscious of the time. So we'll, just to give you a straight or top ambition for something like this ion trap. Underneath here it says an adjustable resolution spectroscopy. If we do our spectroscopy in the center, because I won't go into something called forward Doppler compression and the Doppler shift, we get the nice sort of spectra that I showed you earlier, these super high resolution. If you do it at the end, because of all the motions, it's like doing something that's Doppler broadened or broadened gas, you get far lower resolution. And if you went to town and just illuminated the whole thing, you'd have really, really rubbish resolution. And going, well, you're daft. Why on earth would you wind down the resolution of your experiment? And the trouble is, our experiment is too good at the moment. So trying to find these is lucky. This is yttrium. We know its atomic structure. We have a stable element, and we know where to find its lines. Or you could do a flame test, and you could have a good idea of where its atomic and ionic emission lines are. And we have a good starting point when we zoomed in on this part per billion scale. If you don't have that, this would be like hunting for a needle in a haystack. And you could spend years trying to find your resonance if you didn't know your resonance. So why would you not know your resonance? Oh, by the way, if you want to crudely illuminate things, you use LEDs. So just light up the whole thing. You wouldn't know your atomic structure if you are above atomic number 99. 99 Einsteinium is the last thing we can produce in bulk. And bulk, I mean milligram amounts, or usually microgram amounts from nuclear reactors. After that, everything decays too fast or takes too many neutron captures to get bulk production. You can get tiny trace amounts of fermium and nobelium. You pick those up in atomic bombs, by the way. Well, that's where they were first detected. And actually, courtesy of very similar experiments to what we do, a couple of lines are now known in both fermium and nobelium. For all the rest, no atomic or ionic lines are known. So hopefully you got the headline. You can't go into these systems with part per billion resolution trying to find somewhere where you don't know the first, the first 6 digits. You'll be hunting for weeks trying to find those. So getting a spectroscopy where you can keep all the sensitivity and adjust your resolution, that's going to be very important for our future work. Now, just quickly, I know the time's 2:45, but we started a little bit late. I should live up to my title and say something about, because for me, I'm still second year tutor, there's quite a bit of overlap with what we've been up to research-wise and some things you've had to cope with blended learning-wise, in particular, like what's this last year been like? And not very pleasant, I think, would be an overall summary of having to do things remotely or under COVID restrictions. There's been far too much of that. You should never stare at pictures of yourself. But staring at images of yourself, by the way, makes you anxious. There's a study in the Lancet about that. So endless Zoom meetings staring at yourself is not a good thing anyway. I put a little asterisk here and I said, these experiments work. See you later. So I should pick up, we'll start with the good news or the pros. So we rejigged our experiment to get as much of it to run remotely as we could. And then the local team had to work incredibly hard, or essentially non-stop, running experiments for other people. We ran 3 experiments and all of them were incredibly successful. Now that's brilliant for our usual track record. Experiments are a bit of a hit and miss affair. You can have problems. If you get somewhere on any experiment, you're usually fairly happy. We had 3 really good experiments. I was able to run during the semester. Normally I can only run experiments Christmas, Easter and summertime. Obviously no travel algos and saved all the cost. And that's all in place now. We can exploit it at any time. So yeah, is this how you're going to run forever? Well, much like some of the blended editing, the cons are really significant. This was huge effort. The local people who are based in Finland were working around the clock. The workload under this sort of remote operation scenarios are just ridiculous. None of our UK students, just like the majority of Manchester students, got any lab experience. And that's critical. We work in real experiments, doing real things. You usually walk from where you're working over to the experiment. adjust things, trying building things, trying to get things going. That's part of the joy of the research we do. And trying to stay focus effort when you're sort of back in Manchester, and if you're a year tutor or having to give other lectures or things like that, it is impossible to get a concerted, concentrated time on this. And I say it's much like what we see with sort of blended learning. Just like blended learning, we've now got all of this stuff. So what are we going to do in future? Especially if people hear that it sort of works and maybe thinks, oh, maybe you don't need so much travel money. You should stay at home and you can do everything remotely. Doing it remotely for us or for small scale experiments isn't viable. You can't get training for the students. I'll still be desperate to get back to the lab as soon as I can. For sure, we'll have to seek some sort of hybrid solution in future. I think that'll be like the teaching and learning as well. We now have all these videos created, Blackboard quizzes, and they're there. So going to have to decide what we're going to do with these things in future. So for sure, it'll feature a bit more than it has in the past. But for me personally, I will be very, very much looking forward, despite all the effort. So we put in all of this, it's worked, it's successfully permitted us remote experiments. I'll be happy, maybe just between ourselves, to tell you to get rid of it tomorrow and go back as soon as we can to where we were. Don't take that necessarily as my view on blended learning, but it's not the same. It's not satisfactory. Not satisfactory for the student training. Yes, we ran successful experiments and a number of them. That's all very nice, but that was something I view as under emergency scenario or emergency situation that we had no choice but to do. I think I'll leave it there. What I should thank more than anybody else is my two postgraduates who have worked very, very hard. Again, I say, like all students, under very unpleasant circumstances for this time. So that's Daniel and Sisu. It was most of their work I was showing there. The collaboration involves Liverpool as well as University of Manchester, and that nice lab is the University of Jyväskylä in Finland. Thank you very much.
Thank you, Paul. I think we should be able to unmute ourselves now, I hope. So if we can do a round of applause.
Thank you very much.
Okay, so I suppose we'll go to questions now, if anyone's got any. So you, feel free to put them in the chat and we can read them out. Or if you want to unmute yourself, just go ahead and ask one. I'll go first, just while people have a think, get typing. So I know personally, like, one of the big draws to physics for me was sort of the idea of being able to sort of travel and go to conferences around the world and, work on experiments, abroad. Do you think if there is a move to sort of, especially with the large scale experiments you were talking about, if they were purely sort of done remotely, that could actually put people off going into the field?
I think very much so. Part of going to a lab or a large scale facility is talking to people. It's not just you. I know we're all people will love to talk about their own research boringly and endlessly, but one of the biggest things is meeting people doing other things, meeting when you're younger, other postgraduates, other researchers. Likewise, when you're older, your friends or people you've known for a long time. You meet in an environment that's set up, especially for this, where everybody likes talking about these things, always interested to hear about new developments, or can tell you sort of interesting things about what's going on, what's working. And it's that conversation, or those which are more important than anything else and critical for when you're a student, postgraduate student, is seeing beyond what you do or what your collaboration do, what everybody else. Now, conferences are good for that, but they're very concentrated and you're not going to get around an experiment or going to a working lab and being there for a good few weeks. That's a different world. And it's that I think is really important, was really missing last year.
Yeah, real shame. Got a question in the chat. So I've apologised for the basic question. According to Earnshaw's theorem, you cannot hold charged particles in stable equilibrium under the effect solely of electrostatic fields. What is happening then with the electrostatic cone trap?
Well done for the person who's. I'm sharing, so I can't see who sent that. You're spot on. You can't statically hold. So if we try to hold an ion, say this from an electrostatic field, that would fail. This thing is in permanent motion. So it's very different to other traps you may hear about, like pull trap or penning trap. If you like, we're dynamic, but it's the ions that are dynamic. So the field we're applying are static. It's an equivalent scenario to applying a time varying field on a static system, courtesy of our ion moving. But you're quite correct. There's no way. Well, what we'd like to do is hold this field free or free of particularly magnetic fields to disturb our experiments, completely static. If I was being honest, that would be ideal. We can't do that. You can't do that with an electrostatic field and hold it. That's like trying to keep a ball at the top of a mountain. It'll roll off. If you keep it at the top of a mountain, it's a saddle and spinning, it will stay there. So instead of us spinning our mountain, we keep our ions in motion. So permanent ion motion, and we don't violate Ehrenfest.
Thanks for that question. I was going to ask another one about the precision of the equipment. So I was sort of wondering how you actually, because you were sort of talking about, nanosecond sort of things and even more so, like parts per billion. Like, how do you actually develop equipment that's that precise, that can measure things that precisely?
Oh, there's a joy of lasers. Very, I haven't got a laser picture. When there's a variety of optical components that you suddenly see, like a Michelson, 100 years ago, resolving hyperfine structures. And going, what's going on here? A lot of them relate to if you can hold path lengths very precisely in your device and fit in fixed number of wavelengths, you're up against an integer problem. You can know in number of wavelengths how many you've got in. Actually, ideally, if you can know exactly how many, we're at wavelength 5,620, you have a very, very precise measurement of your distance. And a lot of these devices, you're looking at sort of fractions of a wavelength for controlling it. And our main workhorse, a laser cavity, the finest tuning is achieved by mildly extending the cavity.
Right, okay.
Block mirrors backwards and forwards, not good. Just put a prism in, something called a Brewster plate, at a slight angle, and twist the Brewster plate. And that extra little path difference between the difference between its refractive index and air, slight angle change, and suddenly you're tuning by megahertz in a frequency that's 10 to the 15 hertz.
Okay. I don't know if we've got any more specific questions, but if there was anyone else who was interested in this kind of research, what sort of advice would you give to them, or sort of suggested modules or anything like that, readings, papers?
Yeah, certainly. Follow it will feature in all of the Manchester, so Virgin and beyond. You'll probably see some of the isotope shift, hyperfine structure for sure, because that will feature in your quantum mechanics. The 2 level 4, the exotic nuclei module, there's level 4. We'll pick up on it directly. There'd be suggested readings in that. If I was being honest, some of the research paper is a bit heavy going. I know I'd be picking my own, but my own review paper is, I would say, hopefully accessible. But there's many fields you could look in for something about, say, hyperfine spectroscopy. So looking at these, and it does feature in a whole range of measurements. And hopefully, incidentally, when you're hearing about quantum electrodynamics, your lecturer is going to have to say something like it was shown up by hyperfine structure or lamp shift measurements made by so and so. And if you go and have a look at those, they're very ancient papers to try and read. But any more modern texts on quantum electrodynamics that tells you about the origins of QED will show you where they came from.
Interesting. Thank you. If anyone's got any more questions, speak now or forever hold your peace.
I've got a question about the
okay.
the spectroscopy research. I was wondering if there were any nuclei or sort of nuclei that you're looking at that are specifically interesting or particularly interesting at the moment.
Yeah, no, that's almost exclusively what we target. So what you usually, or what we're usually doing is we know for other reasons, say like that shape change, you may have seen from gamma ray spectroscopy or something else, a telltale sign of something strange has happened. So you're looking at your nuclear, say level structure, and it's suddenly all collapsed or wrong. We have a handful of very particular cases. The one we're probably most interested in at the moment are some ultra low lying isomers. Now, so these are excited nuclear states, but there's one rather famous one in thorium 229 that probably exists around something like 12 eV. So this is just by accident. It's like this for say other people. These should be an MEV or KeV. This is a preposterously low level. It's just a quirk of nature. They're quite low and like hundreds of KeVs or tens of KeVs and heavy elements. But just a quirk of the structure, they're almost sat on top of each other. This could be optically accessible. Now, if you could get into that, that would be very good because this would be the finest ever clock. Now, when you want real precision in the end, what we're all limited by is the frequency standard. And so if you wanted to do something very big, you try and get the best frequency standard. Having a nuclear transition would be the finest. So we have some work going on in that. It's not all of it, but it fits well with our heavy element program. The next one we're actually going to do as a proof of mechanism or proof of or spectroscopy is technetium. So interesting in its own case, that's still at n equals 60, but it's a good demo case because it's a very complicated hyperfine structure pattern, which hurts us in efficiency, and it has no stable isotopes. So if we can prove we can do something that has no stable isotopes, that's at least halfway to going through to somewhere that you have no stable isotopes and no known atomic or ionic structure. So if we can prove that, then you could confidently try and tackle some of these very weakly produced sort of heavies and super heavies and try and get in and do those.
Oh, sounds really interesting. Yeah. Well, thank you.
That's if it works, it'd be great.
If it works.
I won't put it as a probability for that. At least all the Chapman spectroscopy works, and containing our species, and we've proven that even though it's only containing them for a few milliseconds is incredibly useful, and we don't want to go shorter than that because still get to exotic cases.
I see. Oh, thank you.
Yeah.
Okay. So I think if there's no more questions, we'll call it a day. So thank you very much for joining us again.